thank you, Kerry. All right, so the two logistical things first. So I propose for the Piazza to have the final exam be done in the recitation week, or reading week. And I hope that would actually make it easier for both of us, namely that the graders would have easier time to finish grading before the due date. And also you would be working on a final exam without any conflict with the other exams going on at the same time. But if you are ideologically inclined that reading week is supposed to be really reading and no exam should be done, then I would listen to you. So does anybody have objection to this idea? No? No? Everybody happy? Okay, so I see no objections, so let's take that as a final decision. And second thing, this is the part of the homework problem, and I just got a question from Ryan. So when you do the Legendre transform for Lagrangian to Hamiltonian, you need to use every variable in the system for the Legendre transform. And for complex Klein-Gordon field, we are regarding phi and phi dagger as independent variables, and we have the canonical conjugate momentum for each one of them, pi and pi dagger. So you have to do the Legendre transformation for both of them. So please do not forget to use both phi and phi dagger for the Legendre transform when you work on Hamiltonian. Otherwise, you get something nonsensical. Okay, any questions about either of these things? Okay, so let's dive in. So we started talking about complex Klein-Gordon field. So this is the action. And sometimes I write this parameter as kappa squared. And kappa has a dimension of the inverse length. And when you quantize this, we found Hamiltonian is given by what you would expect. But there was also antimatter contribution to it. And we have found that they basically share the same energies, and therefore they have the same mass. And that's why we identify them as matter and antimatter. And when you work out the charge, then this actually turns into just a number operator, but with different sign for matter and antimatter. And this is the conserved quantity, both energy and the charge or number of the particles. So what that means is that you assign +1 to matter particle and -1 to antimatter particle. Which means that even when this number is conserved, that works in a different way from non-relativistic Schrödinger field theory. In the non-relativistic Schrödinger field theory, we had this conserved number, which was the total number of particles in the system. But now we have contributions, both plus and minus, from different particle species. So you can have a process, for example, sending in light. And these are photons, typically gamma rays. And you have some interaction. That will be the production of A particle and B particle. Because this one carries number +1, this one carries number -1, you say total number, defined this way, is actually 0, even though you have two particles in the final state. So initial state have two gamma rays, let's say. So initial state has 0 as far as these numbers are concerned. And 0 is going to 0, so it doesn't violate the conservation law of this charge operator. Yet, you can create new particle species that didn't exist before, because you can still conserve the number the way it was defined as Q operator, when particle and antiparticle actually cancel in the definition of this number. So knowing that this is what you actually get in a homework problem, you can now predict that there could well be this process called pair creation. Namely, you can create particles that didn't exist in initial state, as long as you make them in a pair between particle and antiparticle. And that's the kind of process we have not seen in non-relativistic QFT, but now that we are dealing with the relativistic QFT, you start to see these new phenomena coming up. And indeed, this kind of thing had been observed experimentally, and one of the things we will talk about is actually discovery of antimatter. And I will reserve that when we get to the spin 1.5 particles, because that's the way antimatter was discovered first. So Klein-Gordon field spin 0. We don't jump into that discussion right now, but you will actually talk about see discussions on this kind of pair creation. And if you can create particle and antiparticle in pair, you can annihilate them too. If these particles are initial state rather, and then type go this way now, then you have a particle and antiparticle. If they come together, again the total Q in initial state in that case is 0. Then the particle and antiparticle can annihilate into, let's say, 2 photons. So this is the pair creation. But if you actually do it this way, this is the pair annihilation. Annihilation. Yeah, that's right. It's correct spelling, right? So you can have both of these processes, which we didn't have in non-relativistic QFT. Okay, so this is what we discussed last time. Any questions about this? Everything okay? And now, as you have looked at in the homework problem, we are switching the normalization of this creation-annihilation operators. What I discussed last week was this mode expansion. And now relying on this box. So that these creation-annihilation operators satisfy the Kronecker delta both for A and B creation-annihilation operators. But this box normalization is actually not a very good thing if you are talking about relativistic theory, because if you have a finite size box, but if you go to different reference frame, then as you know, there's a Lorentz contraction that the box size in this direction gets squashed. So size of the box is not a constant in all reference frames. And so this is something you may have done in a homework problem in freshman physics, that when you're talking about this muons reaching the surface of the Earth, then one way to understand it is that in no reference frame, muons are produced at high velocity up in the atmosphere, and because it's traveling fast, there's a time dilation effect, and that's why muon lifetime gets stretched. It lives longer than it should, and that's why they reach the ground. So that's one way to understand why muons produced in, let's say, 20 kilometers in altitude can reach the surface of the Earth. But in the muon rest frame, muon is sitting rest, and the Earth is actually approaching towards the muon. That would be the description of muon rest frame. So in this case, this 20 kilometer distance is actually squashed to something shorter by this Lorentz contraction. And mu1, of course, is at rest, so it lives only 2.2 microseconds, as it should. But because Earth is approaching with a smaller distance than the actual distance in mu1 rest frame, then Earth ends up reaching the mu1 in a shorter amount of time. And that's why mu1 eventually hit the surface of the Earth. So that will be the description of mu1 rest frame. So this is what is called the Lorentz contraction, namely from the particle that's sitting at rest, what is actually moving towards it would look squashed. And so maybe one of the things that is actually being done today is that there is an experiment done at the CERN Hadron Collider, where not only you smash protons on protons, but they also do experiments by smashing lead nuclei on lead nuclei. So this is actually a big object. The lead nucleus contains many protons and neutrons inside, but they come in at relativistic speed. So the description of experiment in the lab frame is like this. They come in like pancakes, and that's a Lorentz contraction. And the description based on this idea really does explain the data. So the Lorentz contraction really does happen. So what it means is that this box normalization is actually not a very good one if you're talking about relativistic QFT. So that's why we switched to a different normalization of creation-annihilation operator based on delta function rather than the Kronecker delta. And then it looks like this, phi of x and t I think there was H or C, let me double check. Yep, that's correct. So the box normalization summed over the discrete spectrum of momenta is now replaced by this continuous sum over the momenta. And as a result, creation-annihilation operator satisfy the commutation relation where Kronecker delta is now replaced by delta function. And because of this 2EP downstairs, is also a normalization factor as a coefficient of the delta function. The reason why we actually keep this extra factor here is that when you have this combination is actually Lorentz invariant. And that's something that's easy to check if you, for example, do a Lorentz boost in z direction, and then this combination undergoes this Lorentz transformation we talked about last week. And if you perform this transformation, that's easy to check that this combination is actually invariant under this. So that's why this normalization is actually a good way of describing a Lorentz invariant QFT. And this is the way we do the mode expansion most of the time. And when you put this 2E here, then creation-annihilation operator is also modified to have this extra factor 2EP in the permutation relation. And this is the way we normally do things. And that's what I'm asking you to do in the homework problem as well. Okay, any questions about this discussion about normalization? Everything okay? And obviously, when you change this normalization of the generation operator, if you define a single particle state with momentum p by creating a particle momentum p on top of the vacuum state, and when you compute the inner product of these states, then we do things as we did before with the Schrödinger field. This is the one particle state P, and here you bring information conjugate of one particle state Q. Then I can change this product of annihilation creation operator by the commutation relation, because the piece I'm adding has this annihilation operator directly acting on the vacuum state, so that gives you 0 anyway. So I haven't changed anything by replacing just the product by the commutation relation, commutator. Once this is a commutator, we know what that is. That's given by this. This is just a number sandwiched between the vacuum state. So that number is the answer of this inner product. So this is the normalization of the one particle state too. So now normalization is changed. Normalization of the creation relational operator is changed. Therefore, commutator is changed. And normalization of states are also changed. But idea hasn't changed at all. So it's still the AP is a relational operator. A dagger P is the creation operator. Okay?
I'm a little bit confused. So phi x, we're describing the field living inside the box, right?
Right.
Because now I'm thinking, say, if I have a particle inside the box, and we're now considering the particle that's moving along with the box, or
Now moving inside the box.
is moving
And
inside.
we also place the periodic boundary condition. So when you actually go to the end of the universe that way, it comes back from the other end of the universe.
Because I'm thinking of which frame I'm actually considering when I look into saying that the.
So in this box normalization, we live in this box, and particles are moving with various momenta inside this box. And you can also have particles sitting in here, but the box is stationary. But if you have a particle moving like this one, and if you want to go to the rest frame of this particle, then you have to let the box move. Then the size of the box changes because of Lorentz contraction. And that's why it's not convenient in Lorentz invariant QFT. Okay? Any other questions? All right, so this is just the normalization stuff, so it's not any sort of big conceptual issue. But now comes to which again you didn't have in non-relativistic QFT. So by now you have gotten used to this idea that the field operator creates particles and annihilates particles. But when you started out this semester, we started out with the creation operator of particle at position x and an annihilation of the particle at position y. And when you compute product of these position eigenstates, just like what we have done now, that's the matrix, that's the inner product. Again, you can replace this by the commutator because I'm not adding anything. And this was still the function. So that is the way we started talking about QFT. This was sort of the beginning of the whole story for this semester. But now that we have this Klein-Gordon field, you can see if this is still true in relativistic QFT, namely that you act phi dagger on the vacuum state. And this is the coefficient conjugate of that, at different position y. And you can work it out because we have this mode expansion. So using mode expansion given up there, you can insert it here. Then you can replace this by the commutator, okay, and work this out. And what you find is actually not a total function, but it's something a little bit more complicated. And this is actually modified Bessel function of the first kind. The name doesn't really matter, but the point here is that when R is large, this function behaves exponentially and again, details don't matter really, but the point here is that even when you have a finite distance between x and y by distance r, it's not zero. It dumps exponentially, but not zero. Namely, this is not really position eigenstate in a way we are used to in quantum mechanics, because slightly different positions are not orthogonal to each other. And again, there's no freedom here, there's no fudge factor, because all we have done is to do the canonical quantization of the field. We follow the rule. We identify the commutation relation between phi and pi. We did the mode expansion, so this commutation relation between A dagger just comes out. And there's no wiggle room there. But once you have done so, you just put it into this expression, work it out, and find that they are not orthogonal. And this is a little surprising. And the only textbook I know that actually tried to explain this is the one by Lipschitz. And the Landau is really famous theoretical physicist, and he lived through the Soviet era. But his institute was actually Kharkiv in northern Ukraine, which had been bombed lately. So it's really destroyed its legacy now. But anyway, so they have the textbook on field theory, and in there they explain this fact in the following way. Now we know in relativity QFT we have this antiparticle. And when you think of nothing, you normally think that there is literally nothing, but it's actually doing this all the time. Namely, here is nothing. And at this time slice, you create particle-antiparticle pair. And when you create particle-antiparticle pair, there's a classical energy. But as we know, uncertainty principle allows us to borrow energy within a finite interval of time. So this is possible as long as within delta t, particle-antiparticle annihilate again, they go back to nothing. So once you accept that antiparticle exists, and once you know physics is quantum mechanical, then this has to exist. Again, there's no way out to that. And if that's the case, particle you produced can travel within delta t at most by c delta t, because c is the speed limit in Lorentz invariant theory, in special relativity. So the particles can travel by this distance before they come back and annihilate to nothing. So what that means is that every particle you have, which you place now in the nothing, so that you have created one particle, but it is actually constantly jiggled by the process that this particle actually sees a particle-antiparticle pair produced nearby as a part of this quantum fluctuation. And sometimes the particle you placed realizes that there is an antiparticle nearby. You might decide to annihilate that one. Then the particle that used to be part of this quantum fluctuation now remains as a real particle. So it looks like this particle that used to be here, all of a sudden, shifted over there. And how much it can shift is basically given by this order of magnitude. So when you say you have placed the particle at position x, well, no matter how good a job you have done so, then this fluctuation of the vacuum is happening nearby anyway. So the particle is sort of jiggling around within this distance given by h bar mc. So it is actually blurred by that distance. So this is what is called the Compton wavelength of a particle of mass n. So this is the Compton wavelength, and this is the inverse of kappa I introduced in the Lagrangian just a minute ago. So the relativistic particle has this sort of intrinsic uncertainty in the position by this Compton wavelength. It is a little blurred. And of course, when you go back to non-relativistic field theory, you send speed of light to infinity, then Compton wavelength goes to 0. So you're back to what you're used to, namely particles at different positions are orthogonal to each other. That's what we learned in quantum mechanics class. That is what we have also seen in non-relativistic QSP Schrödinger field theory. But once the speed of light is finite, then you have this phenomenon, and therefore you don't have strict position eigenstates anymore. When you act the field operator at position x, it does create a particle at position x, but that there is an intrinsic blur in what you mean by the position of the particle by the Compton wavelength, and therefore these states are no longer orthogonal to each other. It dumps exponentially, so if you go over distance well beyond the Compton wavelength, it's practically okay to say they're orthogonal to each other, which is good. That sort of preserves our intuition. But when they're really, really nearby, then this happens. And given that there is one over c downstairs, Compton wavelength is typically very short. If you think about, for example, the electron, we know the mass of the electron. If you put that in, then Compton wavelength is something of the order of 10 to the minus 13 centimeters, which is much, much smaller than the size of an atom, which is 10 to the minus 8 centimeters, right? So for the purpose of talking about, let's say, hydrogen atom, and this is 10 to the minus 8 centimeters, this intrinsic blur is 10 to the minus 13 centimeters, so it practically doesn't really matter. But if you look at the very, very precise spectroscopy of the hydrogen atom, and we will get to that when we talk about spin 1/2 particle called Dirac theory, when the electron is close to the proton, and this blur actually ends up giving you extra contribution to the Hamiltonian of the electron, that actually gives you something called the Darwin term. I don't think that's Darwin of the origin of species, probably a different guy, I think. But anyway, there's something called Darwin term, which actually originates from this blur of the position of the electron. So when you have this, the Coulomb potential, this R is actually the position of electron and position of the proton. But position of the electron is blurred by this jiggling motion over the quantum wavelengths. So you get a correction of the order of the quantum wavelength squared times the sort of how much electron is actually blurred. When electron is blurred, it changes its position, and that's given by this derivative. And the first derivative turns out to give you no contribution. Second derivative is the first contribution of this kind. And you put in the quantum wavelength here. So this is what is called the Darwin term. And you have to include it to get the correct energy spectrum of the hydrogen atom. And this is part of the relativistic correction. So ordinary hydrogen energy levels we talked about is order alpha squared. This effect is order alpha to the fourth. It's a tiny correction, down by 4 orders of magnitude compared to the original spectrum. But this is something you can really measure experimentally, and it's there. So it turns out that this intrinsic blur in the position of the particle is really there in relativistic QFT. So that's yet another interesting effect, which has to do with the fact that the particles in relativistic QFT can be pair created and pair annihilated. Okay, any questions about this? Yes?
When we're talking about relativistic particles, your argument was like delta E and delta T, right? Those still have meaning because they were on the same R reference.
I'm sorry, I didn't get that.
You used delta T in your argument, but they may not be same in all reference when we talk about relativistic particles.
They may not be the same order.
In all reference.
Yeah, so this is of course the heuristic argument. So the actual calculation is this one instead of this one. So this is kind of heuristic interpretation of why there is this intrinsic spread. But in this case, you're basically assuming that you create particle-antiparticle pair in its set of mass frame and let them propagate within time delta t and let them come back and annihilate. So we're assuming that this is in the center of momentum frame. As far as this discussion goes. Is that okay? Thanks for the question. Anything else? Okay. Then I'd like to finish up my model with just one more explanation. Maybe I shouldn't have erased this. So, for complex Klein-Gordon field, we have this mode expansion. And we impose this equal time commutation relation. Well, one thing you can ask is, okay, by using this equal time commutation relation for the coordination, we already assume that this is a boson. This is class 1 even variable. What if we use the anti-commutation relation instead? Then can we quantize Klein-Gordon field as a fermion instead? And I don't go through this argument, but it turns out if you do so, you end up violating causality. Again, causality is a concept strictly within relativistic theory because speed of light is finite. And what happens when you do this? It's the following. So let's say this is t, this is x, and we consider only one dimension for now. This is how a particle travels at the speed of light. And when you actually start with a particle at the origin in space at time 0, if it's sitting around and not moving, it just keeps going this way. The time passes, but particle is not moving. So this will be particle at rest. If the particle is moving at speed v, it would look something like this. But nothing can go faster than the speed of light. So this is the limit. And there's no way a particle can travel this way. So that's what we learned in relativity. What that means is that you can never send information from here to there no information can be sent from this point in space in time to that point in space in time, because that would require superluminal, faster than speed of light communication, which should not happen. And the reason why it should not happen is that suppose you could send information from here to there. But if you actually do a Lorentz transformation to go to another reference frame, it turns out that this place can be transformed to this point in time in space. Then you find that in a different reference frame, it looks like we have sent information back to the past. And that sounds like a problem. Like if you have seen the Back to the Future, you have to worry about your mother getting killed, and then you wouldn't be born. So in the movie, this guy was supposed to sort of disappear, and they barely managed to avoid that incident. So you really shouldn't be able to send signal back to the past. So sending signal faster speed of light is the same thing as sending a signal back to the past. That can't happen. That's why there can never be a communication at the distance, which is more than CT. So what that means in quantum mechanics is that if you have an operator sitting here, and if you have another operator sitting there, doing the measurement of this operator here should be done independently of measurement over there. Now, what we learn in quantum mechanics is that if two operators don't commute, you cannot simultaneously measure both of them accurately. If x and p don't commute, give you one IH bar, you cannot measure x and p accurately at the same time. It's subject to the uncertainty principle. But if these two operators are separated by this long distance where you shouldn't have any communication, the fact that you have measured this operator at this point should not affect anything you do over there. Therefore, any operators at these two positions separated farther than CT should commute so that you can measure both of them without interfering each other. So it turns out that in relativistic QFT, this is the statement of causality. if x, this xt, is bigger than ct. So this distance where x is bigger than ct is called space-length. When, on the other hand, t is bigger than ct, this is called time-length. So the statement is that any operators in QFD where two operators are separated by a space-like distance should commute with each other, namely that measurement of one operator should not affect the measurement of the other operator because there is no communication between the two space-time points. So the idea is that if you have used the wrong statistics, Fermi statistics for Klein-Gordon field, you run into the problem that this doesn't vanish, and that violates causality, because that means measurement at this point is affecting measurement at that point. So you have sent some information faster than the speed of light, which shouldn't have happened. Therefore, that's wrong. So that's the argument here. So if you actually try to quantize Klein-Gordon field as a fermion, you get nonsensical, inconsistent theory, which violates causality. Therefore, Klein-Gordon field must be quantized as a boson. And this is the first example of what is called spin statistics theorem. Namely, Klein-Gordon field is spin zero particle. Spin zero particle has to be a boson. In general, spin integer particle has to be a boson, including spin one, like a photon. We know photon is a boson, otherwise you can't have a laser or coherent electromagnetic wave or radio. So those things are there because it's a boson and you can make coherent state out of them. We talked about that. So it's important that they are bosons, but this is actually not a choice anymore. In relativistic quantum field theory, spin integer particles, in general, must be quantized as bosons. No choice, because otherwise it violates causality. And when we actually talk about spin 1/2 particles soon, I hope, then it turns out the spin half odd particles, including spin 1/2, must be quantized as fermion. Again, there's no choice. If you want to quantize spin 1/2 particle as a boson, you run into a different kind of problem, that energy is not positive definite. And that also runs into other kinds of problems. We will come back and talk about that. So, but in the end, that also leads to some inconsistent theory. So we shouldn't do that. As a result, we learn the spin half odd particles must be quantized as fermions. No choice. That's a spin statistics theorem. So that's yet another thing we learn by going from non-relativistic quantum field theory to relativistic quantum field theory. Without relativity, Schrödinger field could have been either boson or fermion, no matter what the spins of the particle that may be. But once we go to relativity, that's no longer a free choice. Spin integer means boson, spin half integer means fermion, and indeed, that's what we see in nature. Electron is a fermion because it's spin 1/2. So is proton and neutron, they are spin 1/2, and they are fermions. Photon is spin 1, it's a boson. So that's the way it works. We have talked about Bose-Einstein condensate of rubidium atom, and rubidium total spin is 0, and therefore it has to be boson, and indeed it is. That's why it can become a Bose-Einstein condensate. So this is now what we are going to summarize after talking about spin 1/2. But anyway, this is the first occurrence of that phenomenon. Spin and statistics are correlated. They are not independent from each other. Okay, so here I'm just only making a statement, but we'll come back and talk about this. Yes?
Which
Terry?
statement tell us that in this case it's spin zero?
In this case, spin zero, yes. Klein-Gordon field spin zero.
From where can we know it's spin zero?
Okay. So how do we know Klein-Gordon field spin zero? Is that the question?
Yeah.
Okay, so let's talk about that. The simplest argument is that when you create a particle at momentum zero, which means you have a particle at rest. And if you have particle with spin s, then you need to have 2s plus 1 states in its rest frame. But what we have done in this quantization Klein-Gordon field is that you can create zero momentum particles just by acting this creation operator. And you can also create antiparticle, but it has a different charge, so this is definitely a different state. So single particle state with positive charge, there's only one state like that. If there's only one state, then S has to be zero. So that's sort of the quickest argument I can give. More roundabout argument I can give which is probably more correct argument, is that under Lorentz transformation, phi of xt would transform to phi at now at a different coordinate x prime and t prime. We made sure that our action is invariant. So this phi dagger now goes to x plus t prime. And when you do the derivative with respect to original x and t of a function which is now given by x prime and t prime, you have to use a chain rule. Basically that you have to actually do like this one, right? So this is now a function of x prime and t prime. So collectively, I'm calling them x mu prime using 4-vector notation. But x mu prime is related to x mu. This is actually given by Lorentz transformation. So this derivative is what depends on things like gamma and gamma beta. So that means this can be regarded as a 4-vector. And with the derivative and the upper index for the coordinate, we have shown, I think last week, that this whole thing transforms as a 4-vector with a lower index. So this is a transformation of 4-vector with a lower index. Here, I have an upper index. So this Lorentz transformation should cancel between this one and that one, because you're contracting indices, one upstairs and one downstairs. So that's something also we talked about. So it turns out that this chain rule giving you this Lorentz transformation cancels between the two. So the argument inside doesn't change, except for the fact that the whole thing inside is now a function of x prime instead of x. But because this integration volume d cubed x dt as a whole is also Lorentz invariant. So if you do this Lorentz transformation, now everything is given by x prime, both integration volume and the integrand. And this is the integration variable, so dummy variable anyway. If everything is now given in terms of x prime, you can decide to call x prime rather than by x. And then everything goes back to the original action. So this is actually a symmetry or invariance of the action. And we made sure that that is the case when we first wrote down this action for the Klein-Gordon field. So indeed, this is how you can explicitly verify that this is indeed Lorentz invariant. And once you have an invariance of the theory, then we resort to Noether's theorem, because this invariance means a symmetry. Symmetry would lead to conservation laws. And I skipped derivation there, but it turns out that you can write conservation laws in the following way. What we talked about is that for the symmetry of changing the phase of the phi, you have conservation of the current and this is conserved. And once you have this continuity equation, then you can integrate time component of this current and define an operator. And time derivative of this now using this equation, I can rewrite this integrand by this, and using Gauss's law, this can be written as a surface integral. So the charge changes only as much by how much current flows out from the volume. That makes sense, right? So total charge in the system can change only as much as by how much charge flows out from the surface. And when you're thinking about the entire universe, there's no outside, so you can ignore the boundary terms, and then it doesn't change. So that's how we get the conservation law. So this is the case with this change of the phase for the Klein-Gordon field. And you are working out what this charge is using creation annihilation operator right now. And so that you see that this is indeed the number of particles minus number of antiparticles. So you are verifying this conservation law right now. When you extend this argument to a space-time translation, and we will come back to Lorentz transformation in a moment, another symmetry you can have is space-time translation. So when x, this is mu is 0, that's a translation in time. So you go from, let's say, 6 in the morning to 7 in the evening. That's a translation in time. And when you actually take the spatial components, that's the translation in space. So you go from Berkeley to Stanford, that's translation in space. And laws of physics shouldn't change by doing so. So there must be translation invariance of space-time. So that actually is also to a conservation law. And you define something called energy momentum tensor. and this is the Lagrange density. And G mu nu is this plus 1 minus 1 minus 1 minus 1 tensor, metric tensor we talked about before. And this is what is called the energy momentum tensor. And this is conserved. So by following the same argument as we have done over there, I can define this integral and this integral and this equation being the t0 0 plus gradient ti0 vanishes if I take nu to be 0, or if I take nu to be spatial component. So either way, you'll find this kind of continuity equation. So depending on whether you take nu to be 0 or the spatial component I, either of them is supposed to be conserved by same argument up there. And this t00 integral is actually energy or Hamiltonian, if you look at it. Because if you take 0, 0, then this one is actually pi dagger times phi dot dagger. This one is pi times phi dot dagger. So the Lagrange transformation we talked about at the very beginning of the class today is indeed this combination that gives you Hamiltonian. So this is conserved. Energy is a conserved quantity due to the translation invariance in time, which I think you have heard about this in mechanics class. And momentum, total momentum of the system is conserved because of the translation invariance in space. So that's why this is conserved. So that's how you obtain the conservation law of energy and the conservation law of momentum due to the space-time translation invariance, again according to Newton's theorem. And so extend this one step to Lorentz transformation is a little bit technical, so I was not planning to talk about it, but that's something you can do too. And in the case of the Klein-Gordon field, it turns out that you define this tensor and when you take mu derivative of this is conserved. But you can sort of see why this should correspond to the Lorentz transformation. If you specialize this to all spatial components, and I forgot to mention one important aspect of this energy momentum tensor. This is symmetric. If you interchange mu and nu indices, this becomes that becomes this. So the sum doesn't change. This is already symmetric matrix. That doesn't change either. So it is symmetric. And when you look at this component of this, when you choose mu and nu to be spatial indices, and then if you integrate this over space, this integral would become momenta. And then you have xi pj minus xj pi. That's angular momentum. And then you see angular momentum has only this orbital piece, xp minus px, no spin. So deriving what is conserved based on certain symmetry in this Lorentz invariance or rotational symmetry is a part of it. You will find the conserved quantity. And this is the conserved angular momentum now due to the rotational invariance of space. And you can extend this also for the Lorentz boost as a part of the Lorentz transformation when you choose this the index to be 0. But you don't need to go there. Just by looking at what is conserved due to the rotational invariance of space, you can identify the conserved angular momentum operator for the Klein-Gordon field. And if you do so, it is given only by the orbital angular momentum, nothing added to it. And that's the reason why the angular momentum is given only by orbital piece, because there is no spin to the particle, and hence Klein-Gordon field is spin zero. So the first argument was way quicker than this, because you just have to look at the number of states where the particle is at rest. There was only one state, therefore it has to be spin zero. But the true discussion would go through this Heuristic theorem argument that you first look at the symmetry, in this case rotational invariance and Lorentz invariance. For that symmetry, you can identify the conserved quantity, and conserved angular momentum is what comes out from that Heuristic theorem. And once you look at the expression for the conserved angular momentum, there is no spin piece in it. It's just orbital and nothing else. Therefore, this particle doesn't carry spin. And that doesn't turn out to be the case when you apply this argument to spin 1/2 particle like Dirac field, which we get to in a moment. And so then you have actually additional piece, which corresponds to spin as a part of the conserved angular momentum. Then you can really read off that you're talking about spin 1/2 particle, given what the conserved angular momentum operator is. So that's the argument. Does that answer your question?
Yeah.
Okay, good. Any other questions about Klein-Gordon field? Yes, one more.
Okay, just one more, then that would be, we rule out the anti-commutation relation because it violates the causality.
That's right.
But I think causality, we cannot be able to prove that causality is some sort of truth. Because causality.
So you want to show your grandma and you disappear?
No. I mean, if we cannot rigorously prove that when causality is something we can rule out, then maybe we should consider the option that the causality is violatable, because causality is essentially something that we experience empirically. We see things happen from one thing, then after elapse of time, then another thing happens. We build this kind of relation based on experience, but we cannot say that they are truly have some essential link. So if we can explain things better, if we just violate causality, then why not how come we should rule out the causality just because we think it's not true?
Well, okay, so it depends on, I think, your view of physics in that case. So we always take the laws of physics to explain things by having the cause and its effect.
Yes.
And when you write down Newtonian equation of motion, you specify the initial condition, and that will predict how particle moves into the future. So it's always forward in time, cause and effect. That's the way we try to formulate physics. So if you abandon that idea, there may be some other way of describing nature. You can start from scratch, but at least you are abandoning what we have been doing all along in physics. And so whether you can construct a consistent theory that way remains to be seen. And I'm not disputing you, that it's a big jump. And if you make a big jump, you have to go make sure that everything actually still makes sense after abandoning the idea of the causality. I haven't seen such a theory myself, and you're definitely welcome to think about it. But I can predict it's going to be very difficult, for sure. But this is worth trying, yes. That's an excellent question. Any other questions? Even philosophical questions? Okay. So the Klein-Gordon field is spin zero and has to be quantized as a boson. So that was the end of the discussion for Klein-Gordon field for now. And the last thing, before getting into Dirac field, is just having another look at the Maxwell theory. And I think I mentioned this, but I can fully explain it, I think. So let me just try to do that now. So the idea is that Maxwell field also had this Lagrangian. And which was made of the scalar potential and a vector potential. And it turns out that they also form a Lorentz vector, 4 vector, when you look at this combination, scalar potential over C and vector potential. Very similar to what we have done with the energy and momentum. You're putting energy over C and momentum together to define a momentum 4 vector. So we're doing the same thing here. And also the source term, if you like, will be given by this. So you have rho phi minus j a. And if you look at this combination, a mu, j mu, sorry, minus up here, this is actually j mu, a mu. So it starts looking Lorentz invariant because you are summing over the upper and lower indices in this expression. So that's good. The question is, what's happening here? And what's happening here is the following. You define four-dimensional curl using 4 vector A, 4 vector derivative. You define this 4-dimensional curl, which is called the field strength. Where the components with 1 time, sorry, you might not sign up backwards, is 1 over C electric field, if we just work it out. And if you have 2 spatial components, this is the magnetic field. That's right. And as obvious from this notation, this is an antisymmetric object when you interchange 2 indices, because it's a curl. So this object, F mu nu, can be viewed as a 4x4 matrix, which is antisymmetric. So independent components is 4 choose 2, that's 6. Indeed, these 6 independent components are given by 3 components of electric field and 3 components of magnetic field. So they are 6 independent entries altogether, indeed. So F mu nu is a 4-dimensional package of both electric and magnetic field in a single object. And it turns out that this Lagrangian over here can be then written as 1 for F mu nu, F mu nu. And again, upper index is always summed over with a lower index. Upper index is summed over with a lower index, so that this combination is Lorentz invariant. Then Maxwell Lagrangian now looks manifestly Lorentz invariant because it's built of these objects which have always upper and lower index contracted with each other.
Is there any loft factor of mu 0?
Yeah, so I'm actually not sure about this, so I think you're right. I am missing the factor of mu 0.
I think it's
Yes.
denominator.
And also a minus sign. Thank you, Jack. So this mu 0 is there because mu 0 was there. B and Fij have the same dimension, so this has to stay over here. And if you work out everything carefully, there is also a minus sign in front. So this is the way you can write the Maxwell Lagrangian now in this manifestly Lorentz invariant form. So what we have done before was not wasted because the Maxwell's theory is actually Lorentz invariant. And in fact, that's the way Einstein came up with the special relativity. He put such a faith in Maxwell's equation, which predicts the speed of light is constant no matter what reference frame you are in, because it's a combination built out of epsilon naught and mu naught. That's the fundamental constants of nature. So if you put them together, you get a quantity speed of light that is supposed to be common in a low reference frame. He took that very, very seriously, and then came up with this realization that Newtonian mechanics is not consistent with that idea. And as we talked about last week, once you accept the idea that speed of light is indeed the same in all reference frames, as demonstrated by Michael Mori experiment, we had to adopt the idea that time was not common in all reference frame. As you change x, you have to also change t. And that led to this whole idea of special relativity, Lorentz transformation, and so on and so forth. So in some sense, the Maxwell's theory was the reason why we had to make a jump from Newtonian mechanics to relativistic theory. And then so the Einstein, the Maxwell's Lagrange, of course, in some sense by definition, has to be Lorentz invariant because that's where it sort of came from. And indeed, it is. So that's one thing I didn't mention earlier, and I think I'm just throwing this out right now. Any questions about this? Is everything okay? All right. Then we get to speed 1/2. So we talked about speed 0. That's Klein-Gordon field. Speed 1, Maxwell. But we also need speed 1/2 because we need electrons, protons, neutrons, and so on. And this is described by what is called the Dirac field. And Dirac actually came up with this field theory for a wrong reason. And I tell you what the wrong reason was. So what he wanted to do is, again, to come up with a relativistic quantum mechanics. Initial attempt we made led to Klein-Gordon equation, but we couldn't make sense out of it using quantum mechanics because there was no probability interpretation for it. And the reason why Klein-Gordon equation didn't allow was the probability interpretation failed. Which came from the fact that Klein-Gordon equation was second order equation in time. And for the Schrödinger equation to make sense, specifying wave function at the initial time slice should dictate its evolution for the rest of the times. And in order to specify a system with only boundary condition, initial condition at a given time, without specifying time derivative, it has to be a first order differential equation in time. And this is first order. So the Schrödinger equation being first order differential equation in time was crucial for us to take this as a probability wave and define the conserved probability, unitary time evolution, and so on and so forth. So this is what Dirac decided to focus on. Instead of trying to write down Lorentz invariant equation from the onset, he said, well, we really need to make sure that differential equation is first order in time. So that was the beginning of the wrong argument by Dirac. So he wanted to write down equation which is first order in time. But this is the point when Dirac also remembered, of course he was a smart guy, so he knew this. In relativity, you need to treat time and space on equal footing. So if the equation is first order in time, it has to be first order in space too. Now I have a wrong dimension, so I need to put 1/c here. Then it has the same dimension, so at least starts to make sense. But if it's the first order in space, spatial derivative is a vector, has an index, x, y, and z. So what do I do with this? So he said, well, no, we don't know, but because it has to be this way, first order in time to allow for probability interpretation, and first order in time and space, in order to keep space and time on equal footing, well, we have to put in some coefficient here. Alpha. I don't know what that is, but we need something like that. Then obviously, we need also mass coming into the equation. And this one has dimension of one over distance times h bar can be given by a quantity mc with the same dimension. So the equation should look something like this. But once again, you may need to have some coefficient here as well. So let's call that beta for now. So this alpha in beta was unknown at this moment. So this is the Dirac equation. So once again, so it had to be first order in time to allow for probability interpretation. In order to treat space and time on an equal footing, it has to be first order in space. But spatial derivative is vector, so this index xyj has to be contracted with something else. So let's say we introduce some coefficient here called alpha for that purpose. We need a mass term too, so to have the correct dimension, it has to come with mc, but there may be also coefficient, so let's put beta in there. Now we want to make sure that this is consistent with the idea of E squared being C squared P squared plus M squared C to the fourth. And as we always do, H bar d dt is supposed to be energy. H bar derivative is supposed to be momentum. So that cancels I. So we have an equation like this one. And in order for this equation to reproduce this, we would like to fix what alpha and beta should be. So in order to go from here to there, I multiply this thing in the square bracket by a piece which has this the minus sign in front. And by multiplying this on top of this one and write it out, I'm feeling I may be making some mistake. I think this is also minus sign.
You substitute the IH bar nabla into P. There are like minus sign.
Ah, okay, thank you. So here I have minus sign. And I should have also put minus sign here when I introduced this beta matrix initially. So, no, this is just a typo, sorry about that. And in order for this equation to be consistent with what we expect for the energy of relativistic particle, I multiply this whole thing by this one, so that if I multiply this on top of this, I find C over C squared. And this is alpha p plus mc beta with positive sign here, negative sign here. So the cross terms cancel, and then I get alpha p plus mc beta squared. In order for this to be the same as p squared plus m squared c squared, then we can derive some requirements on what alpha and beta should be. So this one squared should become p squared. So what that means is that alpha I, alpha j, plus alpha j, alpha I has to be 2 delta ij. If this is true, then this is alpha I pi, alpha j pj. And that's a symmetric combination between pi and pj, so that's half of this. So that means that's delta ij acting on pi pj, so that becomes p squared. So that's good. For this square to become this, we need beta squared to be 1. That looks okay. But then this cross term has to cancel because there's no p's that goes like pmc. So that means alpha I and beta have to anti-commute. So this is the requirement for this equation to make sense. And that's the Dirac's argument. But to satisfy this requirement among alpha and beta, it turns out the only thing he could do was to say alpha and beta are 4x4 matrices. And this is written in 2x2 block form. This is the Pauli's matrices. And if you actually take this, then you can easily check that this satisfies those requirements. So when he wrote out this equation, the alpha and beta were unknown, but in order for this equation to reproduce the standard mass and momentum relationship in relativity, this alpha and beta had to be matrices, like this. So this is actually a 4-component object. And Dirac was happy with this idea initially, because if you have multiple components, now you have a room to put in spin 1/2, namely the particle at rest has 4 components with it, and that actually ends up being electron, spin up, spin down. And as we already learned, relativistic QFT comes with antiparticles. Positrons spin up and spin down, and they are the 4 components, which corresponds to the 4x4 matrix over here. So far so good. But that actually eventually leads to yet another problem, and that's when we have to grapple with the idea that Dirac equation still doesn't make sense as a single particle quantum mechanics. It turns out that this also had to be made field theory. So Klein-Gordon equation didn't make sense as a probability equation, and therefore we promoted to field theory, then everything made sense. Dirac equation intended to allow for the probability interpretation because it's a first order in time. So it does lead to sort of right structure of the multiplicity of states, but leads to a different kind of problem called the negative energy problem. And in order to solve that problem, it turns out that you have to promote this field theory too. So in the end, everything turns out to be QFT instead of quantum mechanics. So that's the argument I go through on Friday. And probably repeating from here on once again to make sure that I get the message across. And then build QFT of the Dirac theory at the end of the day, which turns out to be the correct theory of spin 1.5 particles. Okay? Any questions? Alessandro?
I have a question. The second term in that expression is a matrix, right?
Yes, matrix.
Then also the first term must be a matrix, so E
Yeah,
divided
so
by
this
C.
is proportional to identity matrix. in
Okay,
that
okay.
case. Yes, thank you. Any other questions? Okay, see you on Friday.